Thank you. So I would like to thank all the organizers for giving me the opportunity to speak here. So we'll be concerned with converging sequences of graphs and the limits. And so I will consider combinatorial graphs. And as you shall see, a natural source for such sequences are actions by automorphism of rooted trees. And then in a second part, we'll consider a statistical physics model on such sequences called the Abelian Sandpile Model. So we will work in the compact space of rooted graphs with uniformly bounded degrees, and notice the pointed house of Gromov topology. So in this topology, a sequence of rooted graph converges to the limit graph G rooted at V if balls in Jn centered at the roots and of growing radius coincide with balls of the same radius in J centered at V. So an example of such convergence are covering sequences of graphs. But before looking at more concrete instances, let me first reformulate this convergence in a measure setting. So if we are given a sequence of graphs but without any rooting and we are interested in its convergence, we can choose a root in each Gn uniformly at random. So this defines a sequence of probability measure on X star, and the weak limit rho of this sequence is called the random weak limit of the sequence of graph Gn. So in other words, rho is a probability distribution on the limits of the sequence of graph Gn, but now considered as rooted graph and for all possible choices of root in each Gn. So many examples of graph converging in the house of Gromov sense are provided by actions by automorphism of rooted trees. So let T be the binary rooted tree so that the vertices of the nth level are identified with binary words of length n. So any automorphism of the tree must preserve the root and hence the levels of the tree. Thus, given some subgroup gamma of automorphism of the tree, we associate with its action on the successive level of the tree a sequence of graphs which are called the Schreier graphs of the action, which are defined as follows. So the nth Schreier graph has for vertex set the vertices of the nth level of the tree, and two such vertices are connected by a direct and labeled edge if there exists some element in the generating set of the group mapping one vertex to the other. So we would like to understand the convergence of such sequences of Schreier graphs. And to do that, we'll consider a special class of automorphism acting on the tree in a self-similar way. So the tree has a self-similar structure as the subtree rooted at any vertex is isomorphic to the whole tree. Thus, given some automorphism G of the tree, we can describe its action on the tree recursively as follows. We first indicate by a permutation how it acts on the first level of the tree, and then for each vertex of the first level, we indicate how it acts on the subtree rooted at that levels. Noting that the restriction of the automorphism to that subtree is again an automorphism of the whole tree. But now, if we consider some subgroup of automorphism of the tree, so it is not sure that the restriction of an element of that subgroup to some subtree of the tree will be again in the subgroup. So this leads to the following definition, which is due to Grigorchuk and Nekrashevich, and saying that a group gamma acting by automorphism on the tree is self-similar if for all its elements and every vertex of the tree, the restriction of the action of that element to the subtree rooted at that vertex is in the group. So an interesting example of a self-similar group is the Basilica group introduced by Grigorchuk and Juk in 2002. So it is generated by two automorphisms which have the following self-similar structure. The automorphism A fixes the vertices of the first level, then act as B on the subtree rooted at 0 and as the identity on the subtree rooted at 1, whereas B permutes vertices of the first level, then act as A on the subtree rooted at 0 and as the identity on the subtree rooted at 1. So here is the Schreier graph of the action of the Basilica group on the binary tree, on the first levels of the binary tree. So in order to keep the picture clear, I've omitted the edge and vertex at the labelings since the third level. So let me mention here that an interesting consequence of Nekrashevich's theory about self-similar group is that under certain conditions, the Schreier graph provide approximating sequences of compact fractal limit spaces corresponding to Julia sets of rational functions. And in the case of the Basilica group, the corresponding function is the polynomial z squared minus 1. However, in this talk we shall be interested in details in the Hausdorff-Gromov convergence of these graphs. So, Schrödinger graphs are covering sequences. And the inverse limit of such a sequence corresponds to the action of the group on the boundary of the tree. The connected component of the inverse limit are called the orbital Schrödinger graph, and they are limits in the Hausdorff-Gromov sense of the finite Schrödinger graph. Namely, given some point psi in the boundary of the tree, there's a natural choice of roots along the infinite ray in the tree corresponding to that point. And then the sequence of Schrödinger graph, of the finite Schrödinger graph rooted at these vertices, converges in the Hausdorff-Gromov topology to the orbital Schrödinger graph containing the point psi in the boundary. So why is it interesting to consider such sequences of Schrödinger graph and their limits? So on one hand, as they form approximating sequences of Julia sets, they can be used for computing spectral Laplacians on these limit spaces. They can be also used to compute spectra of infinite graph if you use Hausdorff-Gromov convergence. From a probabilistic point of view, this graph provides new examples of random weak limit. And it is of interest to study this measure with the hope of understanding how it reflects different properties of the group acting on the tree. So one can ask, for instance, whether this measure is atomic or not. We can study the geometry of the graph supporting it by looking at the number of ends, their growth, and so on. And still from another point of view, many statistical physics models are usually defined on a sequence of finite graphs exhausting some infinite lattice. On the other hand, we know, for instance, by studying percolation Keeley graphs, that it is fruitful to consider such models on some other sequences of graphs. So it may be interesting to consider such models on, for instance, covering sequences of Schrödinger graph arising from such self-similar actions. So our first result is a detailed analysis of the Schrödinger graph of the Basilica group. And so we give a topological as well as a measure theoretical descriptions of all possible limits. And it turns out that a limit graph can either have 1, 2, or 4 ends. And as the action of the group on the boundary of the tree is ergodic, there is one typical case for the number of ends with respect to the uniform distribution on the boundary of the tree, which turns to be 1. Equivalently, the random weak limit is supported by one-edged graphs. Moreover, it turns out that there are uncountably many isomorphism classes of one-edged graph, each of them but one being itself uncountable. And a consequence of that is that the random weak limit of the Basilica Schrödinger graph is non-atomic, which actually seems to be the case for a large class of self-similar groups. So here are some pictures of how different orbital Schrödinger graphs of the Basilica group look like. So we have one-edged graph, a four-edged graph here, and two-edged graph here. So we turn now to another aspect. So provided now with sequences of graph converging to some interesting limit, we'll consider a statistical physics model on these sequences called the Abelian Sandpile Model. So the Sandpile Model was introduced in the late 80s by three physicists, Bach, Tang, and Wiesenfeld, with the aim of providing an analytically tractable model with features of self-organized criticality. The self-organized criticality of a model means that the internal dynamics of the model leads it to a non-equilibrium or critical state without external tuning of any parameter. So after its introduction, the model was widely studied by physicists, among them by Deepak Dhar, who established several combinatorial and algebraic properties of it. In particular, he proved that the model is abelian, which is a crucial property making the model mathematically tractable. So we start by defining the model on a single finite graph, and then in a second step we will consider it on converging sequences of graphs. So given J, a finite connected multigraph, the model consists in configurations encoding the repartition of an amount of grain of sand or chips on the vertex of J, and of local transformation rules between successive configurations. Namely, if there is some vertex on which the number of chips is bigger or equal to its degree, the vertex is declared unstable and it is fired. And firing V consists in passing along each edge incident to V a chip in direction of the corresponding neighbor. So this firing process may result in the apparition of new unstable vertices, and if so, we continue this process. So clearly, if the total amount of chips among the vertices of the graph is too large, the firing process will never stop. So to avoid this problem, we introduce a so-called dissipative vertex, P, so that the chips reaching P will leave the game. And since the graph is connected, it ensures that the firing process eventually stops. The abelian property of the model observed by Dar means that the stable configuration that we reach through a sequence of firings is independent of the order in which unstable vertices are fired. So in order now to understand what happened with the model on a long run, we consider a subset of the stable configuration, which are the recurrent configurations. So there are different ways of characterizing them, but the easiest is by considering a Markov chain on the set of stable configuration defined as follows. So given a stable configuration eta, we drop an extra chip on a randomly chosen vertex. And if the configuration eta with that extra chip is unstable, we let it stabilize into a new stable configuration eta prime. So this sequence of firings transforming eta with the extra chip into the stable configuration eta prime is called an avalanche. So it is straightforward to check that the Markov chain is irreducible, and hence there is a unique stationary distribution mu supported by the set of recurrent configurations. And moreover, it turns out that mu is a uniform distribution. So now the main mathematical question about this model is to prove its criticality, meaning that the correlation between sites situated far away from each other is high. And this is typically done by exhibiting asymptotically a power law decay over its statistics. So we consider now a sequence of finite graphs converging to some infinite graph G. And the criticality of the Abelian Sandpile model appears through the occurrence, statistically, of many large avalanches. Therefore, it has sense to consider the model, and especially the dynamics of avalanches, with respect to the Markov chain we have, to the stationary distribution of the Markov chain we have just defined. More precisely, we consider the following random variable, encoding the mass of the avalanche triggered by adding to some recurrent configuration an extra chip on a fixed vertex. So by the mass of the avalanche, we mean the total number of distant vertices fired during the avalanche. So of course, instead of considering the mass, we could consider any other quantity encoding the size of the avalanche. Then we say that the ASM of the sequence of graph Gn converging to G is critical if the limit, as the graph becomes larger and larger, of the probability of observing an avalanche of mass m decays as a power law for some exponent delta that we call the critical exponent. It turns out that proving criticality and moreover computing the critical exponent is a difficult question, and in spite of many numerical experiments, the criticality of the model on the Euclidean lattice ZD is not proven, and rigorous proofs exist only for regular trees. So there were also some numerical experiments on some other graphs, for instance on the Sierpinski gasket. So the question now is how to develop methods for proving criticality. So it would be desirable to understand how the geometry of the underlying graph is related to it. And from this point of view, it may be useful to consider the model on some other sequences of graphs. So we have studied the Abelian Sandpile model on the sequence of the Basilica-Schreil graphs. And so recall that the random weak limit of that sequence is non-atomic and supported by one-edged graphs. So exploiting this latter fact, we were able to answer rigorously to the question of the criticality of the model in this case. Namely, given some point psi in the boundary of the tree, the model on the sequence of Schreil graphs converging to the orbital Schreil graph containing the point psi is almost surely critical, with critical exponent exactly equal to 1. Thus, we have exhibited an uncountable family of graphs on which the criticality of the model as well as the exact value of the critical exponent are rigorously proven. And even if these graphs are not quasi-isometric to the square lattice, they share properties with it as they are one-edged, four regular, and of quadratic growth. Thank you very much for your attention.